Okay, in today's lecture, we're going to cover the section 6.8 material on the divergence theorem. And the divergence theorem is a result which we can consider as a higher dimensional version of Green's theorem. So if we recall, Green's theorem gives us a relationship between the line integral of a vector field around a closed curve in the plane and the double integral over the region enclosed by that curve. So in a similar way, the divergence theorem is going to give us a relationship between a surface integral of a vector field over some surface, or a flux integral, and a triple integral over the solid region enclosed by that closed surface in space. Now, before we can state the divergence theorem, we need to introduce a little bit of terminology. So let us start with the definition. So we would say that a solid region E in space that can be expressed simultaneously as a type 1, a type 2, and a type 3 region is called a simple solid region. Now, the boundary of a simple solid region E is some closed surface, and we're going to make use of the convention that the positive orientation over this surface is the outward orientation. So that is the orientation which we will give this surface is the one for which our unit normal vector n is pointing outward from the solid region E. So as an example of some simple solid regions, we could consider regions which are bounded by ellipsoids or spheres, by rectangular boxes, tetrahedrons, bounded by cylinders. We can also think of as simple solid regions. So these are all typical examples of what we would say is a simple solid region. So now that we have this terminology, we're ready to state a result known as the divergence theorem. And so here's what it says. Let us suppose that we have some region E, which is a simple solid region, and the boundary of that region is some surface S, which has the positive or outward orientation. And let us suppose that we have some vector field F, whose component functions have continuous partial derivatives on some open region of space that contains the solid E. So that is, this vector field is relatively nice over our solid region E. Then the surface integral of the vector field F over the surface S, which is the boundary of our solid region, is equivalent to the triple integral over the solid region E of the divergence of that vector field with respect to volume. So again, the divergence theorem is giving a relationship between the surface integral of a vector field over a closed surface S in space and the triple integral over the solid region which is enclosed by that surface. So let's look at some examples making use of the divergence theorem. Its primary application is to evaluate surface integrals over closed surfaces that might be a little difficult to evaluate using our surface integral formula. So in our first example, we are told use the divergence theorem to evaluate the flux of the vector field F, which is x cubed, y cubed, z cubed, across the unit sphere x squared plus y squared plus z squared equals 1. So we're supposed to evaluate this flux integral over a sphere, and one way that we could do this would be to try to do it directly. We could parameterize this unit sphere by making use of spherical coordinates, and then use our formula for the flux integral over a parametric surface. But we saw in our earlier chapter 6 work, well, the formula for the integral, flux integral over a parametric surface requires us to find partial derivatives of the vector function describing our surface, taking the cross product of those partial derivatives, expressing our vector field in terms of the parameters, and then taking its dot product with that cross product and evaluating some double integral. So it gets to be quite tedious to do it directly, but now that we have the divergence theorem, let us convert our flux integral to a triple integral over a solid region. Now, the first step in applying the divergence theorem is to calculate the divergence of f. So our first step will be to find the divergence of f, which recall is defined as the dot product of the gradient operator with our vector function, f. And we get, for the first part of our divergence, the partial derivative of our first component, x cubed with respect to x, which would be 3x squared, plus the partial derivative of our second component, y cubed with respect to y, which would be 3y squared, plus the partial derivative of our last component, z cubed with respect to z, which would be 3z squared, or if I factor out a 3, I'm left with the sum of x squared, y squared, and z squared. Now, applying the divergence theorem, let's say by the divergence theorem, the flux that we're interested in, which would be the surface integral over the surface S, which in this case is the unit sphere of our vector field, is equivalent to the triple integral over the solid region E enclosed by that unit sphere. So that would be the unit ball, all points inside of the sphere of radius 1, of the divergence of F with respect to volume. So here we have the triple integral over the solid region E, and we found the divergence of F was 3 times the sum of x squared, y squared, and z squared. We're integrating with respect to volume. Now, to evaluate this triple integral, we need to set this up as an iterated integral. And since our solid region E is the region enclosed by the unit sphere, that is the unit ball, that suggests that we would probably want to use spherical coordinates to evaluate this triple integral. So setting this up as an iterated integral in terms of spherical coordinates, our outer integral with respect to theta would be from 0 to 2 pi, since we want a full rotation around our sphere. Our second integral with respect to phi would be from 0 to pi. We want the full sphere, so moving from the positive z-axis to the negative z-axis, moving from one pole of the sphere to the other. And then our innermost integral with respect to rho would range from 0 to 1, since this was a unit sphere, a sphere of radius 1. And now let's convert our integrand to a function in terms of spherical coordinates. So we had a constant 3, and then the sum of x squared plus y squared plus z squared in terms of polar spherical coordinates is rho squared. So we have rho squared. And then our differential of volume on the end in terms of spherical coordinates is given by rho squared times sine of phi d rho d phi d theta. All right. So here, let's start evaluating this integral. Now, to begin with, we can use our shortcut in evaluating these iterated integrals. We notice that the inner two integrals all involve functions of rho or phi only, and the limits of integration are constant. So our outermost integral with respect to theta from 0 to 2 pi we can think of pulling this constant function out in front of that integral, and we have the length of our theta interval, which is 2 pi times the constant with respect to theta, which would be the inner two integrals from 0 to pi and 0 to 1. And then simplifying our integrand, we have 3 rho squared times rho squared gives us rho to the 4th times sine of phi d rho d phi. So now, to evaluate this integral, we could think about pulling our constant 3 out in front with the factor of 2 pi. So this would give us a 6 pi. And then our inner integral with respect to rho, well, we can pull out anything that is a constant with respect to rho. So that is our sine of phi and d phi. I can pull out in front of this rho integral. And I'm left with the integral from 0 to pi of sine phi d phi. And then I still have my integral from 0 to 1 of rho to the 4th d rho. So we have 6 pi times the antiderivative of sine phi would be negative cosine of phi, which we're evaluating from 0 to pi. And the antiderivative of rho to the 4th is 1/5 rho to the 5th, which we're evaluating from 0 to 1. So we now have 6 pi times, when we evaluate cosine phi at pi, we have cosine of pi, which is -1, but the negative out front gives us a +1. And then we subtract what we get when we plug in 0. So we have negative cosine of 0, or -1. Subtracting that -1 gives us a +1. And then evaluating our 1/5 rho to the 5th at 1, we have 1/5 minus, when we plug in 0 for rho, we get 0. So altogether, we're left with 12 pi over 5 for the flux of that vector field across the unit sphere. So here we see that this is much easier than trying to first parameterize that sphere and then evaluate the flux integral using the formula that we had from section 6.6. So the divergence theorem, very useful in evaluating flux integrals over closed surfaces. So let's look at another one. In this last example, we are asked to use the divergence theorem to calculate the flux of the vector field f of x, y, z, whose component functions are given, across the surface, which is the surface of the solid, which is bounded by the cylinder, x squared plus y squared equals 9. So a circular cylinder of radius 3, centered along the z-axis. And this solid is also bounded by the planes z equals 0, that is the xy plane, and the plane z equals y minus 3. So let's try to visualize our solid region here to see what our surface looks like. So in this example, our surface is the surface of the solid bounded by our cylinder, x squared plus y squared equals 9. So a circular cylinder of radius 3. It's bounded below by the xy plane, that is z equals 0. And then our cylinder is extending upward along the direction of our positive z-axis, and then it's bounded above by a plane z equals y minus 3. So notice that does not involve the variable x. So if I slice this surface, this plane, with any fixed value of x, that is with a plane that is parallel to the yz plane, I get a line. So this plane when I slice my cylinder through with it, will intersect this cylinder in an ellipse, sort of this offset plane. Will slice my circular cylinder in this curve, and that upper plane is the graph of z equals y minus 3. So my solid region here is the region E inside of those surfaces. Now the surface itself that I'm trying to find the flux across is the boundary of that solid region. So if we think about just its surface, not counting the interior, that would be the surface S that we're trying to integrate over. Now, if we were to try to do this directly without applying the divergence theorem, we see that our surface S consists of 3 piecewise smooth pieces. So it consists of this bottom disk, so we would be looking at the downward flux through that surface. This little upper disk, which is enclosed by an ellipse, we're looking for the outward flux across that surface. And then the sides of it are bounded by this cylinder. So I would look at the flux across each of those 3 subsurfaces, and then I would have to take the sum of those in order to do this directly. But now we're told that we can make use of the divergence theorem to do this, and we see that it works out much easier. So let's look at how we would set this up. Our first step in evaluating or applying the divergence theorem is to calculate the divergence of our vector field. So here, taking the partial derivative of our first component function with respect to x, we have 0, plus the partial derivative of y squared with respect to y gives us 2y. And then we add the partial derivative of our last component, e to the xy, with respect to z, which would be 0. So the divergence of this field is just 2y. So by the divergence theorem, the flux that we were interested in, which would be evaluated as the surface integral over the surface S of our vector field, is equivalent to the triple integral over the solid region E enclosed by that surface of the divergence of our vector field with respect to volume. So let's see what we have here. To evaluate our triple integral, we want to set this up as an iterated integral. So here, let's write it out. First, we had the triple integral over E, and our divergence we found to be 2y, integrating with respect to volume. So to set this up as an iterated integral, let's think about our solid region E. We see, well, it's bounded on its sides by a circular cylinder and above and below by 2 planes, the graphs of functions of the form z equals. So this suggests that we would probably want to use cylindrical coordinates to set this up as an iterated integral. So using cylindrical coordinates, our outermost integral with respect to theta would range from 0 to 2 pi, since we're looking at a full rotation around that circular cylinder. Our next integral with respect to r would range from 0 to 3, since we were working with a cylinder of radius 3. And our innermost integral with respect to z, well, here z was bounded below by the xy plane, or z equals 0, and it was bounded above by the plane z equals y minus 3. Now, if we're making use of cylindrical coordinates, y, recall, is given by r sine of theta. So our upper value for z, y minus 3, is now r sine squared, r sine of theta minus 3. Now converting our integrand here was 2 times y, changing that into a cylindrical function, we have 2 times y, which again is r sine of theta. And then the differential of volume in terms of cylindrical coordinates is dz. And then the outer 2 integrals with respect to area in terms of polar coordinates is r dr d theta. Remember, we pick up that extra factor of r when we switch to polar coordinates or in the plane or cylindrical coordinates in space. So here, let's start by grouping the r terms together. We have the integral from 0 to 2 pi, and from 0 to 3, and then from 0 to r sine theta minus 3, and our function is 2r squared sine of theta in the order dz dr d theta. So our innermost function, 2r squared sine of theta, is a constant with respect to the innermost integral z. So integrating a constant function over an interval gives us that constant times the length of that interval. So we have the integral from 0 to 2 pi and from 0 to 3. Our constant was 2r squared sine of theta. That is a constant with respect to z. And then we multiply by the length of the z interval, which was r sine theta minus 3 minus 0, or just r squared, r sine of theta minus 3. Then we're integrating in the order dr d theta. So distributing this 2r squared sine of theta, we have the integral from 0 to 2 pi and from 0 to 3, the function 2r cubed sine squared theta minus 6r squared sine theta in the order dr d theta. So here, evaluating our inner integral with respect to r, we have from 0 to 2 pi, antiderivative with respect to r, we would have r to the 4th over 2 sine squared theta minus 2r cubed sine theta, evaluating from r equals 0 to 3, and then integrating with respect to theta. So we have now the integral from 0 to 2 pi of, evaluating at r equals 3, we have 3 to the 4th, or 81 over 2, sine squared theta, minus r cubed, or 3 cubed is 27 times 2 would be 54 sine of theta. And then we subtract what we get when we plug in r equals 0, which is 0. And then we're integrating this with respect to theta. So now to evaluate the antiderivative with respect to theta, this first term, sine squared of theta, we have to think of in terms of 1 minus cosine of 2 theta over 2. We're going to make use of our double angle identity. So this becomes the integral from 0 to 2 pi of our 81 halves times half of this quantity gives us 81 over 4 times 1 minus cosine of 2 theta minus our 54 sine theta d theta. So now taking our antiderivative of each piece, well, the antiderivative of 81 over 4 is 81 over 4 times our variable theta, minus the antiderivative of 81 fourths times cosine of 2 theta is 81 over 8 times sine of 2 theta. And then the antiderivative of negative 54 sine theta is positive 54 cosine theta. And we're evaluating here from 0 to 2 pi. So plugging in 2 pi for theta, we have 81 pi over 2. Plugging in 2 pi for theta here, we have sine of 4 pi, which is 0, and then plus 54 times cosine of 2 pi, which would be plus 54. And then we subtract what we get when we plug in 0 for theta. So we have 0 minus sine of 0, which is 0, and then plus 54 times cosine of 0, which gives us a 54. So our plus minus 54 cancel, and we are left with 81 pi over 2 for the flux of that vector field across this surface S, which is the surface of that solid region E described in the problem. So in this last example, again, we see the divergence theorem provides an easier way to calculate flux across a surface rather than have to consider the surface of the solid in 3 separate pieces and then evaluate the flux across each of those surfaces and take the sum. We could evaluate this using the divergence theorem using a triple integral. And although triple integrals aren't trivial to evaluate, this was a much easier approach than trying to evaluate the flux over each of those subsurfaces. So the highlight of this last section is we can use the divergence theorem to calculate the flux of a vector field over a closed surface by converting it to a triple integral over a solid region enclosed by that surface.